Back everybody, I hope you enjoyed your lunch. So, just in this document here, which you have, this is the schedule for today, okay? So, we've been through this one, we've had lunch, and we're back now until 3 o'clock. What I will do is lecture up until 3 o'clock. I'll finish one lecture and then start the next one. That will give us more than enough material for you to look at the workshop questions which we have just here. So in the final session of today, which will take about 45 minutes, you can make some progress with your question sheets. I will move amongst you and help you with those questions, and that will bring us to the end of today. And then from that basis, we can move forward to looking at the more advanced things tomorrow. Right. Let's get that. So before the lunch break then, we arrived at this point, where we were talking about crystal field splitting in lanthanide complexes, questioning the assumptions behind this free ion approximation, and we found, especially at low temperatures, it is important to question these assumptions, because the f orbitals in a complex can split in the crystal field, and they do this in the context of these MJ states here, and for dysprosium this is the result. Things split into a series of doublets which you can regard as a crystal field splitting. Okay. I then took you through these bullet points, which I'm not going to read out in detail again, but one of the key features that came across here, because we're talking about f orbitals, they have a very strong angular dependence. Okay, so magnetic anisotropy is an important part of the electronic structure in a very general sense, but especially so for designing single molecule magnets. So the question I left you with right at the very end of the lecture was, how can we use coordination chemistry to manipulate the electronic structure of these compounds? Okay, how can we manipulate the anisotropy to design a single molecule magnet? So hopefully by the end of this course, you will start to answer these questions yourself and be able to put forward sensible ideas for designing a single molecule magnet. But to try and answer this question in the early stages, we'll return to a familiar picture, which is this one here, the 4f orbitals. Excuse me while I have a drink of my tea. Okay, so what we have here is the general set of 4f orbitals, which I mentioned in yesterday's lecture. So just to remind you of a few key properties, clearly these orbitals have a very strong angular dependence. They have 3 angular nodes, which I think you can see here, okay, just about with the colouring, so 3 of them. And in terms of modern parlance, in the context of molecular magnetism, the shapes of these orbitals have started to be described using 2 terms. Okay, one of these is oblate, and the other one is so-called prolate. Okay, so you will hear me talk about these quite a lot. If you go away and read the literature in this area, you will see these terms used quite frequently. So if we take this orbital here, okay, this is the fx x squared minus 3y squared. This orbital stretches out into the xy plane. It stretches out into the xy plane, and for that reason it is said to be oblate in shape. Okay? So if you want a more common analogy here, it's a little bit like a pancake. Okay, so you start with a spear and you squash it, it stretches out in this direction like that. Okay, that is said to be oblate, okay, without the cream. Then you have an orbital such as this one here, the fz cubed orbital, and I think you can see very clearly that this orbital is being stretched in this direction, along the z-axis in this particular case, and that is said to be shaped in a prolate fashion, a little bit like a cigar standing on its end. Okay, so that's a classical description there. So I will use these terms interchangeably. Interestingly, the lanthanides, in terms of their electron density, so by electron density what I mean is, let's just say for gadolinium, which is an F7 species, each of these orbitals will have 1 electron in it, and the combined density of those comes out as being spherical on average. If you change to something like cerium, for example, which has only 1 f electron, we can put it in this orbital and say the electron density is like this. So you can do that for all the other lanthanides, the net impact produces these qualitative structures here. Okay, I emphasize qualitative, the more quantitative picture I will give you on the next slide. But you can see as you move through this series then the shape does start to change. So here it's oblate very clearly, here it's still oblate. By the time you get to neodymium, now it's kind of neither oblate nor prolate. Okay, so you're getting an averaging out of the orientations. By the time you get to promethium, it's now starting to look a little bit like this, and by the time you get to samarium, it's stretching out even more. Europium doesn't appear here because its ground state is said to be officially non-magnetic, J equals 0. Then you get to gadolinium, which is perfectly spherical, and then when you get to terbium, you've gone 1, 2, 3, 4, 5, 6, 7, now you're back to this one again. So the electron density of that configuration, if you like, is determined by the imbalance in the population. So terbium-3 is related to cerium-3. There's a difference of 7 F electrons between these two. So terbium is said to be oblate, as is dysprosium. Holmium, a little bit like neodymium, is slightly distorted, but not very much. Erbium is very clearly prolate, as is thulium and ytterbium. And by the time we get to the end here with lutetium, which is a closed shell species, once again we're now back to a spherical distribution. So broadly speaking, we can classify the electron density in lanthanide cations in 3 ways. Well, 2 ways are important, okay? So all of these here are said to be anisotropic, okay? That means the electron density, the magnitude of that, depends in the direction you're moving. That much is pretty obvious. These 2 here are completely isotropic. So I told you on the previous slide that what we want is magnetic anisotropy. So at least in principle then, every lanthanide apart from these 2 should in principle be a candidate for a single molecule magnet. Which is reflected to some extent in things like spinorbitals and gravity. So what do you need to know from this? In order to try and enhance it. So this illustration here is now represented in blue. These yellow dots are the donor atoms of a ligand. So if we're talking about ligands in a lanthanide complex, we're talking about electrostatic interactions between metal and ligand. So let's just say, in a very general sense, we have our 3+ cation here and a ligand here that is formally a 1-. If you arrange 4 ligands above and 4 ligands below, you have a significant negative charge above and below and some electrons in the middle. So what they will do is distort to try and get away from this negative charge. Okay? The ligand charge affects the F electron density in a way that makes it distort. And if you get those ligands in the right place, you can enhance the anisotropy. So this is the ground state with the spin-orbit coupled magnetic moment pointing up and pointing down. What does that correspond to in terms of what we've seen before? Okay, it actually corresponds to these 2 systems. Okay, but with an analogous picture for terbium. Okay, that's what we're looking at here. The excited state is shown up here, higher in energy, where if we flip from one MJ state to another one, the electron density in that state, in that shape, changes its orientation. This is shown here in the idealized case, where it's gone from being oblate in the XY plane to being prolate in the Z direction. So it's effectively become perpendicular. I emphasize that this is an ideal situation just to try and clarify the point. But here you can see the electron density is now interacting much more strongly with the ligands, and therefore this is destabilized. So the electron density kind of circulates in this direction, and this projects the magnetic moment in a perpendicular direction, similarly shown here as well. So you can see then, as you change the value of Mj, in whichever state you're looking at, you change the orientation of your magnetic moment. Okay, so that's why it's important to populate one of these states ahead of another. What is the general message here? Well, if we're talking about a coordination compound with the metal ion and donor atoms, the way in which these donor atoms are arranged around the metal is critical. This means that the symmetry of your coordination compound is absolutely critical. Okay, so as a coordination chemist, what you are trying to do is to control the symmetry of your ligand environment in a way that maps onto the F electron density. Okay, if that sounds difficult, it's because it is. It's a very exacting task. You need to design your ligands really very carefully indeed, and at some point in this course, I will give you some examples of where people have been very successful at doing it. So that's the situation for an oblate ion. Next we'll move to look at a prolate version. So the situation with prolate is different. Here with oblate we have what's said to be an axially symmetric environment. The ligands are placed above and below this metal line here along the magnetization axis here. If we go to a prolate ion, so randomly chosen as ytterbium 3+, an F13 species, this is the prolate electron density. Now, to enhance the anisotropy in this species, you place the ligands not above and below, but actually around the middle. So you've gone from an axially symmetric environment to one that's equatorially symmetrical. So that's a different approach. It's complementary depending on the lanthanide. So these are two different versions of the same thing. One magnetization up, one pointing down. And here you can see in this one, now the electron density is lying in the equatorial plane. The electrostatic repulsion is stronger, therefore this one is destabilized relative to the ground state. So your choice of lanthanide is critical, your choice of ligand is critical, and the symmetry with which these ligands are arranged around the metal is also absolutely critical as well. So we're now starting to get a flavour for the things that you need to do to make this work in order to observe the desired effect. So this, if you like, is in a very general sense. Just to try and give you a little bit of a clearer insight into what the electron densities actually look like alongside a real example. What you see here in this graph, so this is the series of lanthanides with their ground state term symbol. So here is dysprosium. Here is the electron density for the various Kramers doublets. So for dysprosium we've seen that there are 8 pairs, 1, 2, 3, 4, 5, 6, 7, 8. We said that the ground state for dysprosium is defined by 15/2, which is this one here, 7.5. So the electron density in the ground state of dysprosium is calculated to look like this. It may not be so easy to tell from here, but it is effectively shaped like a pancake. It's quite a thick pancake, but definitely oblate in terms of the electron density. So what it's easy to do is to address the electron density in the ground state because that is fixed. The problem is, of course, when you come to look at the excited states as well, because you can see as you move through the shapes here, if you remember that energy level diagram I showed you where the doublets went up like this, this is what they actually look like in terms of theoretical calculations. So here it is oblate. Here, what is the shape? It's kind of hard to define. Here it's different. Here it's now starting to look prolate. And here it's starting to change shape again. So you can take the ground state into consideration very easily in most cases, but the excited states also matter. And this is where it becomes really extremely difficult to create a ligand environment that will match onto the ground state and to the excited state. Okay? I'm not trying to make this more complicated than it needs to be. I'm only really trying to illustrate that it's difficult to address. So there's the situation with dysprosium. You can see qualitatively in the ground state, terbium is fairly similar. Okay, this is shaped like an M&M. Again, pancake shaped here as well. So this is a real compound. This is terbium in here. If you look back at this picture, okay, 4 donor atoms around terbium. Here you can see 1, 2, 3, 4 donor atoms around terbium. So this is a real manifestation of this general picture. This particular compound is very famous for a number of reasons, but in particular, this was the very first lanthanide single molecule magnet, published in 2003 by a group in Japan. And what you have in this thing is terbium sandwiched between 2 so-called phthalocyanine ligands, okay, which have been in the literature for many, many years. But you have 4 atoms above, in terms of donors, nitrogen's here, and 4 atoms below, and they're arranged in a high symmetry environment. Actually D4D symmetry, if you care about things like that. So with that arrangement of ligands, what the aim is to stabilise this electron density here and create a large gap between these two states and all the others as well. Because it really is engineering at a very microscopic level using coordination chemistry. And actually the results, at least for terbium, are shown here. So you can see right at the very bottom here that the primary aim has been achieved. What you want to do is to stabilise the NJ states with the maximum value, which has been done in this case here, okay? So plus minus 6 is the maximum value for terbium, which is shown here. And then the energy gap between the ground state and the first excited state is actually quite substantial. There's nothing in between. Conveniently, the first excited state is defined by plus minus 5 NJ. Okay, so that fits in with the pattern of increasing regularly. But when you look past this, you go from plus minus 6 to plus minus 5 to 0, to plus minus 1 to plus minus 2, 4, and then 3 are basically the same energy. Based on a very simple approximation, I don't think you would expect that. And actually, it highlights that controlling the relative positions of all these crystal field levels is really extremely difficult. In some cases, impossible. If we move now to look at dysprosium, which I've told you about in lots of detail, with dysprosium, I'm not sure if you can see this very clearly or not, the ground state is defined by 13/2, not by 15/2, which is what you would ideally want. Okay? 15/2 is actually here, about halfway up the scale. 13/2, then 11, then 9, then 15, then 7, 5, 3, and 1. So you may have a well-defined idea of what you want to do with the coordination chemistry, but in many cases, nature will have a much better idea of what it wants to do. Okay, so you're really trying to fight against that. And I won't go through all this in detail, but what you do find is that the ordering of these energy levels in terms of the NJ values is not always easy to predict. In many cases, it's completely impossible. So that is the main message to take away from this. We can talk about things in an ideal setting in terms of we design a compound, we synthesize it, we make the measurements, and everything matches up exactly according to our predictions. That typically does not work out to be the case. The trick is, can you work out why it isn't behaving the way that you want to, and then re-engineer your system to deliver something closer to what you would design? And essentially, that is what the remainder of this course will focus on. So just to finish this section, what we are doing here, I think you will agree, is taking a much closer look at magnetic anisotropy, how the electron density manifests itself in relation to the ligands. It's critical for a number of reasons, but it's pretty obvious, I guess, that the energy of a magnet really does depend on the orientation of the magnetization. So this is relative to a set of axes imposed on the molecule by you, the observer. Okay? So what you need to do is choose your axes carefully, consider things such as symmetry, group theory, and how this might impact on crystal field splitting. We'll come back to this. This is not just true for molecular magnets, but it's also true for real magnets that you carry around on a daily basis. The general principles are completely the same. The critical point is that because anisotropy is a well-defined directional property, if you get all your molecules behaving in the same way, this is the thing that will lead to magnetic hysteresis, particularly with coercivity. If your molecule has magnetization with a preferred direction, okay, it is a magnetized material, which is what you want. And therefore, to drive that magnetization away, it should be necessary to apply something called a coercive field, which I'll tell you about in the next lecture. In terms of the anisotropy, what are the units of anisotropy? Well, there aren't any really. It's a well-defined concept, but it's not something that you can measure directly. But you can express this in terms of things like electron G values, typically determined by EPR spectroscopy or by ab initio calculations. So we've talked about things in terms of oblate electron density and prolate electron density. A different way of trying to quantify that is in terms of these G values. So for oblate electron density, you're said to have something called axial anisotropy, which is then oriented along the z-axis, by definition. Again, we're going to come back to this for sure. And this is said to be easy-axis anisotropy, which is a term that you may know about if you've read something about single molecule magnets. So for each MJ state, and I'll take the example here again of dysprosium, there is a theoretical limit for the G values. Okay? So because we're on the z-axis, for the ground state of 15/2, the theoretical limit is that your G values in the XYZ direction are equal to 0, so nothing in the XY plane, and your GZ direction is 20. If you compare that to a typical G value for a transition metal, which is about 2, okay, you can see that the anisotropy with dysprosium is massive compared to what you would get with a transition metal. So the anisotropy really is very, very big indeed for lanthanides. You can do likewise for the other MJ states, and you can do exactly the same thing for most of the other lanthanides as well. What we're not going to do is talk about methods of determining G values because it's slightly beyond the scope of the course, but EPR spectroscopy is the experimental way of determining them, or ab initio calculations. So what we've done there really is talk about the ingredients that you need to make a lanthanide single molecule magnet. What we are going to do now is move on and do a compare and contrast with the lanthanides and transition metals to see how the design considerations can vary a little bit. So that should be the end of this one, I think. Yeah, okay. Okay. So we're now going to delve into single molecule magnetism in quite a lot more detail. So the way that I've so far built up this course on lanthanides is to talk about some of the basic principles of transition metal chemistry and do the contrast with the F-block. Okay? We'll talk about some very simple terms: paramagnetism, anti-ferromagnetism and ferromagnetism. We'll come back briefly to spin moments and orbital moments. We'll talk a little bit about the Zeeman effect, zero field splitting and things like that. Very briefly, I will mention statistical mechanics in passing. I realise that doesn't get most people excited, okay, so I'm going to keep that quite brief. We'll then talk about basic properties of magnets, such as the magnetisation, the susceptibility. We'll then move on to look at systems in which we have more than one magnetic centre and how they can interact with each other. And then we'll come back to our friend magnetic anisotropy. This will give us a very firm foundation to move forward to look at single molecule magnets. I think it's important to emphasise the role of manganese here. Okay, manganese, if you like, is the recurring theme amongst transition metal single molecule magnets and the way that dysprosium is for lanthanides. And we'll do a compare and contrast here again with lanthanides. Moving on towards the end to look at some recent literature in the form of case studies to illustrate where the field is right now. Okay, so a simple paramagnet is something that you probably know a little bit about from lecture courses here. They're also referred to as Curie paramagnets. So this is a molecule, a complex, a compound, whatever, with one or more unpaired electrons. Because it has an unpaired electron or more, it has a magnetic moment, and because there are no special cooperative effects or anything like that in the system, these moments, represented by arrows here, are oriented completely randomly in the absence of a magnetic field. Okay, completely randomly, meaning that the sample has no net magnetisation. In terms of magnetic field, okay, in terms of terminology, the two symbols represent the same thing. Okay, but nobody can really seem to agree on which is which. Physicists seem to prefer B, and magnetochemists seem to prefer H. It doesn't really matter what the symbol is, okay, but if you take a bunch of paramagnetic centres and switch a field on, they will align with that field, okay? The magnetic moments will align with the field, and that is the situation there. Your sample then becomes magnetised. When you switch the field off, okay, because these individual magnetic moments depend on the external field, as soon as you switch the field off, they go back to where they started. Yeah, in my version of these slides, okay, this arrow is red, not black. That's a Curie paramagnet. How does that differ from an actual magnet? So ferromagnetic materials, iron oxide, neodymium magnets, samarium and cobalt magnets, are also referred to as permanent magnets or hard magnets, and their magnetic moments are spontaneously aligned below a certain temperature, which characterises the material known as the Curie temperature. Okay? So for things like magnetite, this is room temperature and above. Above this Curie temperature, okay, thermal energy feeds into and agitates the individual magnetic centres such that their moments become randomly oriented above a certain temperature. So it's a different regime to what we would get with a Curie paramagnet. So really what you're trying to do with a single molecule magnet is create a molecular system that does this at a useful temperature, which is difficult, but we'll come back to it. So, to characterise a ferromagnet and a paramagnet, one of the traditional experiments, tried and tested method, is to measure the magnetisation as a function of the magnetic field. Okay, so the magnetisation we can define as a total magnetic moment of a particular sample that you're observing. If we first of all consider a paramagnet, okay, so zero field equals zero magnetisation, pretty obvious. As you increase the field, okay, the magnetisation starts to build up in a steep fashion. Then as you increase the field further still, the magnetisation increases at a slower rate and eventually becomes level, okay, where you reach a saturation point. I'll come back to that. For a paramagnet, when you switch the field off, it goes straight back to where it started from, and if you change the field to be in the opposite direction, you get a mirror image curve. Okay, rather an inverted curve. That's a paramagnet. A ferromagnet is different. So you start at field zero and you magnetise up to this point, but when you reverse the field, rather than going back to where you started, you end up here. Okay? You end up in a situation where the applied field is zero, but the material has retained magnetisation. Okay? That is a characteristic signature of a ferromagnet. The value of the magnetisation shown here is the so-called remnant magnetisation. It's what's left over after you've removed the field. If you want to drive the magnetisation back to zero, you have to work to do that. So you're at this point now, magnetised in zero field, you apply a field in the opposite direction, and eventually you reach a point at which the field starts to drop, and then you approach magnetisation of zero at a specific field. At this point, the field is referred to as the coercive field. Okay, so when you coerce somebody, you push them into doing it. Okay, so what you're doing here is that you are coercing your material to go back to a state in which it was not magnetised. That is a well-defined signature of the magnet. And then what you can do is cycle around again like this by magnetising, demagnetizing, so on and so forth, so that you generate a series of loops. And these loops are referred to as hysteresis loops. So this term hysteresis here, as the name implies, is connected to the history of the sample. That means the current state of your material depends on what's happened to it in the past. Okay, so it is magnetised here because previously you've applied a field to it. So the properties then of a paramagnet and a ferromagnet are clearly very, very different indeed. This is the reason why ferromagnets are so useful for things like information storage. So here your material is magnetised in a well-defined direction. Here your material is magnetised in the opposite direction. So this gets you into the idea of a 1 and a 0, binary information, bits, and hence information storage. That's where this comes from. Okay, so to drive the magnetisation back to zero requires a coercive field, and typically speaking, the bigger this field, the stronger the magnet. Is how this works. The only thing I've not mentioned at this stage here is there is a constant factor throughout this entire experiment, which of course is the temperature. Okay, so these hysteresis loops will change their position as you change the temperature, which, as we'll see for single molecule magnets, can be something of a problem. Okay. So, where does this magnetisation come from? We have already discussed this a little bit with the lambda matter. Okay, obviously, it comes from the unpaired electrons. It comes from the spin contribution and the orbital contribution and the way in which these things interact with each other. Okay, so static moment arises from unpaired electrons. We have the spin angular momentum, which is a purely quantum mechanical effect. So here is an electron spinning on its axis, okay, generating field lines and projecting a magnetic dipole in a direction with a value of plus or half. So this is not telling you anything you don't know already. And here we have the opposite situation where the spin is going the other way and now pointing down. So the idea is the motion in this direction here projects a dipole in that direction. Then of course we have the orbital contribution, which corresponds to electron motion in physical 3D space, which if you wish you can regard as electrons moving between orbitals, which we definitely already talked about. This is a very convenient representation. It's worthwhile pointing out just in passing, something that hopefully you know already. You need to get away from this idea of an electron being a dot that spins around a particular point. Okay, it's just a convenient pictorial representation. Okay, electrons don't actually have physical dimensions. Okay, but this is just one way of getting it across. Okay, so this is something we've already talked about today. Crystal field theory applied to transition metals, d orbitals split by coordination of ligands. This is an example for octahedral symmetry. We have 1, 2, 3, 4, 5 d orbitals. 3 go down in energy, T2G. 2 go up in energy, EG. Okay, everybody knows that. The size of the splitting, so this part here, depends on the metal oxidation state, dictates the overall electronic configuration. For transition metals, we have things like high spin or low spin, depends on the metal oxidation state and on the nature of the ligands that we have in this system. So, for transition metals, things come out looking like this. Again, I'm not going to go through this in intricate detail because transition metals are what you already know about. Let's just take one example here, copper 2, which is a D9 species. So 1, 2, 3, 4, 5, 6, 7, 8, 9. One unpaired electron means a spin multiplicity of 2, and the unpaired electron can be in this orbital or this orbital, so we have an orbital degeneracy of 2, therefore it is an E term. Okay? If you want to apply the same analysis to all the other ones, you can do that. Nickel is a triplet A, chromium 3 is a okay? Something clearly does happen, okay? But if we take a situation when we're talking about the origins of magnetization, and the graphs I've just shown you in the previous slide, in a magnetic field of 0, a particular value of S has 2s plus 1 degenerate ms states. Okay, this is the spin multiplicity that we've already talked about. So if you take a triplet T term or a triplet A term like this, they both have one unpaired electron, which means there are 3 allowed values of ns, plus, minus 1 and 0. In the absence of a magnetic field, those 3 states are degenerate. Okay, their orientation is not affected by the environment per se, but if you place them in an external magnetic field, this is what resolves the degeneracy. So, by definition then, if we have a moment that is anti-parallel to the field, so field this way, moment that way, that has a well-defined energy, okay, that is higher in energy than the other. So one goes like this, higher in energy, one like this, lower. The 0 energy we can define, if you like, arbitrarily almost, as the energy of the term in 0 magnetic field. Seems obvious, but I think it's worth pointing out. So what happens? Looks like this. So the graph that I've drawn here represents both of these because it's defined by this part here and also these things. So we have 3 states which in a field of 0 are degenerate. And I said here 0 energy defined as energy of term in 0 field. Okay, that is this one here. That's the 0 energy. And the energy of each state is given by this simple expression here, in which the energy is equal to the product of the spin, the G value, the Born magneton, and crucially, the magnetic field. What we're doing here with this graph is looking at how the energy of the system changes as the field increases. Okay? The reason why that's significant is because the rate at which the energy changes with respect to the field gives you the magnetization by definition. This is a definition. So conveniently then, the ms states in this one are plus 1 and minus 1. Sorry, minus 1 and plus 1. And you can see then, as they evolve, with the field, the splitting between them gets bigger. This type of splitting diagram here is referred to as a Zeeman splitting diagram. So how energy levels evolve on application of a magnetic field. So G then is this Landé G factor, which is constant for the system you're looking at, and these things can be determined by EPR spectroscopy. For an electron on its own, this is the G value, 2.0023. Any deviations from this indicate magnetic anisotropy. Okay, we've already seen for dysprosium that the G value can be in the region of 20 in the Z direction, so that's huge. So, what we can say then, as we move forward, if we have a spin-only system with G equals 2, let's say octahedral nickel 2, so this is, got a couple of slides, nickel 2 is here, S equals 1 triplet A. Okay, so what we've done here, G equals 2 gives us these two terms here. This is the ground state, this is the first excited state, and this is the second excited state. We can calculate the energies of these terms using fairly simple expressions. So this calculation here is this expression, just with the right numbers put in. Okay, so G is equal to 2. This is the product of the constants, okay, and this is the value of the field. So what we're saying is a small magnetic field, 0.1 Tesla, or 1000 Ørsted, or Gauss, if that's what you prefer to use. For a single ion, okay, the energy of that term comes out as being this one here, 1.85 times 10 to the minus 24 joules. What does that mean? Why is that significant? Well, if we are at a temperature of 1 Kelvin, the thermal energy available, Boltzmann's constant in temperature, is this, 1.38 times 10 to the minus 23 joules. So when we compare this number with this number, we can see it's almost 1 order of magnitude bigger. Okay, the thermal energy at 1 Kelvin is almost 1 order of magnitude bigger than the splitting between the Zeeman levels. What that means in a situation like this, at low field, is that the population of these MS levels is effectively equal. Okay, because the energy gap from here to here is small relative to the amount of thermal energy available. So these MS levels are equally populated. Okay, if you want to work out the actual populations of the individual levels, you can do that using statistical mechanics, and this is stuff that's been known for well over 100 years as well. But these simple expressions you may well have encountered in the context of your physical chemistry thermodynamics lectures. Okay. And again, for those of you who are trying to write this down as you go along, don't worry, you will get all the slides and have all the information available. Okay, so that's the situation with a very small magnetic field. Each MS state has a different orientation with respect to the field. Okay, the field has a well-defined orientation. They have their own well-defined orientation. It may be different to what the field is. So what that basically means is that the net magnetization in a very small field is also small, which I guess is pretty obvious. So what these individual spin states are trying to do is align with our very small field. But the problem is that too much thermal energy is available, so they cannot do that. The thermal agitation in the system means that they can work against the external field in a small field. What about when we move to a much larger field? So now we've gone up by a factor of 20 compared to the energy separation. What we've done in our diagram here is move from somewhere in this position maybe to somewhere over here. So the energy gaps are getting larger, and that clearly has implications for the relative populations of three levels. And in fact, when the field is sufficiently large, these MS levels are not equally populated. What we start to see is a distribution. Indeed, the distribution will be dominated by the lower energy term. Okay, that means the net magnetization in the system will now be bigger than it would be in a smaller field. Okay, which may seem obvious, but it's may well worth pointing it out. If we keep going with the field, if we make it larger and larger, so the energy gaps become very substantial, the population of this level and certainly of this level diminishes really quite dramatically, such that this term only really starts to represent the magnetization of your sample. What that means is that the magnetisation will start to change, sorry, the energy will start to change in a linear fashion with respect to the field. So it becomes a constant rate of change. That manifests itself in terms of what you measure in terms of the magnetisation as a so-called saturation value, which I'll show you now on the next slide. So that comes out looking a bit like this. So the two graphs we have here, this is the one from the previous two slides. Variation of the energy of the system with increasing magnetic field. And what we have here is something that you would typically measure experimentally using the squid magnetometer, for example, is how the magnetisation of the sample varies as we increase the field. Okay, so zero field equals zero magnetisation. Then, let's just say we have 6 objects in our sample. As we increase the field, okay, it's possible to populate them all, but not equally. The lowest energy term dominates, then the next one, then the next one. And then the magnetisation starts to increase with a certain amount of curvature. Then we go again. Now the field has increased to such a level that it's no longer possible to populate the highest energy state because the thermal energy is not enough to overcome the barrier. So the population of this level begins to increase, and this one also starts to be populated in preference to this one. So what we're seeing is a non-linear distribution of spin populations, hence this curve here starts to become a little bit more prominent. And then as we increase the field further still, now the energy gaps are significantly larger, so it's no longer possible to populate this level. The only one that's populated now has a well-defined energy depending on the field. So the rate at which the energy changes with respect to the field is a constant, and hence the magnetisation becomes a constant as well. So for those of you involved in magnetic measurements, when you are seeing your curves go like this and then start to level off, what you're observing is a saturation magnetisation, which you can interpret in terms of one of these simple Zeeman splitting diagrams. Okay, so the energy right at the end is well defined, and the only variable is the magnetic field. So what I've just showed you there is a generic case for a spin large S of 1. The same thing happens for all the other spin states for transition metals, but obviously the absolute values of the magnetisation will increase as we increase the spin. So here we could have titanium 3+, here it's nickel 2, here it's chromium 3, here it's high spin iron 2, here it's high spin manganese 2. Okay? The curves have the same qualitative shape every time. Rapid increase in low fields, then it starts to become a little bit less steep in the increase, and eventually you approach the saturation. You interpret it with exactly the same type of diagram, sometimes more complicated depending on how many states you have, but nonetheless that's it. Okay. So by the time you get to the end here, your saturation magnetisation, when only one of your states is populated, the magnetisation is said to be saturated, and it is possible then to equate approximately your saturation magnetisation in terms of 2 simple parameters. Okay, the G value and the total spin, the units of Bohr magnetism. So this turns out from an experimental perspective, when you collect data like this, which is very, very simple to do, it can provide you with convenient measure, if not a direct measure of course, of the number of unpaired electrons in your system. So that's very useful to do. Okay, those of you who are involved in these types of measurement will already be doing it by inspection anyway, I guess. Okay, so that was how the magnetisation changes expressed in terms of the energy and the magnetic field. The rate at which the magnetisation changes, so this bit here as well, can be shown here. Okay, so the rate at which the magnetisation changes with field also gives rise to a fundamental property in magnetism, which is the susceptibility. So this Greek symbol chi is the magnetic susceptibility, and there is more than one way of defining this. Mathematically, this is the strict definition, but in terms of a more convenient phraseology, the extent to which this magnetisation can be induced in a sample is said to be the susceptibility. Okay? The extent to which your sample is susceptible to a magnetic field. The units are EMUs per mole, electromagnetic units per mole, or more commonly centimetres cubed per mole, which may seem slightly unusual, but for some reason it may seem to be so. So, what you do notice with these magnetisation curves, in very simple cases, is when you're at very low magnetic fields, they look almost linear. Okay, not quite, but close enough. So that this expression, rather than being a derivative, becomes a simple ratio of the two things. Okay, so this is telling you that the susceptibility is not going to change its orientation. The Curie law, okay, which is connected to paramagnetism in its simple sense, tells you that you can relate susceptibility to temperature in an inverse fashion, and the constant proportionality defines your material. Okay? So the chi parameter is inversely susceptible to temperature, which kind of makes sense. Again, the sample should become more susceptible to a magnetic field as you lower the temperature. And to get a material characterized, you can determine C from the data. So, specific to a certain material, as temperature decreases, more susceptible to the magnetic field. For a perfect paramagnet, okay, these things do exist, so things with small or non-zero or zero orbital contributions. Your Curie constant can be expressed in terms of Boltzmann's constant, Avogadro's constant, the G factor, and the term that reflects the spin of the electron. So nothing too complicated. And in fact, you can simplify this such that your Curie constant can be expressed as this simple ratio here. G squared over 8 multiplied by S plus 1. So this is a quick and convenient way for extracting key information on a molecular magnet based on data that is actually very easy to measure very conventionally. So let's have a look at that now in a little bit more detail. We can rearrange this. So the chi-T product, okay, which is very often how susceptibility data is represented because it gives you extra information, is equal to the Curie constant is equal to this. What that means is that if the Curie law is going to hold, okay, then the plot of chi-T versus temperature should be constant. Should be a constant. Now, to try and give you insight into why the Curie law might not hold, I'm going to make a comparison which may not seem immediately obvious, but this possibly goes back to chemistry, so maybe even in high school. I don't know what the situation is in India, but certainly when I was in high school, we studied the ideal gas. So obviously, the ideal gas law tries to express the properties of a gas in terms of a few variable parameters: the pressure, the volume, the temperature, the amount of the material, and the constant. There is, I think, a magnetic analog of the ideal gas law, in which you can regard the pressure as equivalent to the magnetic field and the volume as equivalent to the magnetization. So what you know about the ideal gas law is, one of the assumptions is that molecules don't interact with each other in an ideal gas law. Hopefully that's familiar too. What the Curie law assumes is that magnetic centers don't interact with each other. Okay, so we know that in gases, molecules do interact with each other. They have to interact with each other. It's just the way things are. And in magnetic molecules as well, there is an interaction. It may not be so easy to predict what it is, but it will be there. So in a real gas, you have interactions between molecules. In a real molecular magnet, you have interactions between magnetic centers, and that means you observe deviations from Curie-like behavior, and they become most prominent at lower temperatures. That is also true with gases as well. If you take a gas and cool it down, the properties become more liquid-like, right? The interactions between molecules are stronger, and that's when you start to see the bigger deviations away from ideal behavior. Exactly the same applies to a molecular magnet. So what we can do is take the Curie law and modify it in terms of something called the Curie-Weiss law, and what that does, if you like, is tweak the denominator in which susceptibility appears. So previously, we defined the material in terms of Curie constants. If that material shows behavior that deviates away from ideal Curie behavior, we're getting so-called Curie-Weiss behavior, and now we introduce a second constant, which again is particular to the material. Okay, so you can define the material now in terms of two constants and not one is constant. So this term theta here is measured in units of Kelvin, okay, but it is not a temperature. It is a constant specific to a material, not a temperature. If you have theta measured in units of Kelvin greater than 0, your material is defined as a ferromagnet. And if you have theta less than 0, it is defined as an antiferromagnet. Okay, that tells you something very quickly about your material. Okay, we'll finish soon in time for tea. So what I thought I'd do is just show you in terms of some data what you would actually get from something like this. This is an example with a spin about half, with a G value of about 2.2. This could be 0.2, I guess. But this is a theoretical situation in which we have two sets of data. Again, we have some dashed lines which show the Curie material and some solid lines which show material following the Curie Weiss. And we have the data expressed in two ways, as chi, or as chi to the minus 1, reciprocal chi. If we take the Curie law first, which is this one, you can see that your value of chi, which is this one here, the dashed line, straight line through the origin. And negative Weiss constant defines an antiferromagnet. So this is actually very useful information. So you have theta value now of minus 1, which defines your material in addition to the Curie constant. Okay, so this is really very simple information that you can extract something from pretty quickly about your material, which will then help you develop a more complicated model in terms of interactions between magnetic centers. Okay, so what does that get us? Okay, I think we'll stop there, because magnetic exchange is quite a big topic that we need to talk about. Probably best if we take a tea break. Okay? That's it, time for tea. Thank you.